Welcome back, guys. In this video we're going to be talking about finding the slope of a surface in any direction. In the last video we found the slope of a surface in the x direction and in the y direction with our partial derivatives of f with respect to x and y. We learned how to compute those and then how to plug in numbers and interpret them as slope of a surface in a given direction. In this section, it's very similar. We're looking at slope of the surface given by z equals f of x, y in a particular direction. So let's say, actually this should be x. Let's say that this is x naught and that's y naught. So this is x naught, y naught, 0 here in the xy plane. And maybe we want the slope of the surface in the direction of this vector. Maybe it goes that way. Well, remember what we did when we were finding the slope of the surface in the x direction and the y direction. When I wanted the slope of the surface in the x direction, I took the plane y equals y naught and I intersected that with my surface. And that created a curve on the surface, and I found its slope at the point x naught, y naught in the x direction. And then when I wanted the slope in the y direction, I took another plane, x equals x naught, and I intersected that with my surface. And then I looked at the slope of that of the curve of intersection at the point x naught, y naught on that plane. So what we're doing here is actually very similar. I want to create a plane that is aligned with this vector and also passes through this point. So I'm going to try to draw a plane. It's parallel to that vector and passes through our point. And that plane is going to intersect our surface on a curve. So maybe our plane looks like this. I'm trying really hard to make it parallel, but it's hard to draw. We do the best we can. Okay, maybe this is what it looks like, roughly. So the rest of that plane is behind the surface. I don't know, maybe it's in front of it. It's very MC Escher-esque. Okay, so at x naught, y naught, we go up to the surface, and it turns out we're going to be right here. At this point, x equals x naught, y equals y naught, z equals f of x naught, y naught. What if I want to find the slope of the surface in this direction? And the direction again was given by this vector that was in the xy plane. It started at x naught, y naught, of course z equals 0, and it headed that way. So we want the slope of the surface where this plane intersects our surface. We create this curve, and then we find the slope of the surface right there. We want to know how much does z change as we go 1 unit in this direction. Now a lot of students say 1 unit, why 1 unit? Well, remember how we interpret the derivative of z with respect to x. So let's say I've got the partial of f with respect to x, which we could also notate this way using subscript notation. Sometimes people use z as the dependent variable and write z sub x. This is the slope of the surface in the z direction. The units for this, let's just say, for example, maybe the slope of the surface in the x direction right here is, let's say, -3. I don't know what it actually is, but let's say it is. Well, this tells me that z goes down by 1 unit for every 1 unit change in x, instantaneously at that particular point. We always use the units of the numerator divided by the units of the denominator, because remember, derivatives are just slopes of secant lines, but then we let the denominator get infinitely close to 0, and then we got the slope of a tangent line. So that's what this was. So if you calculate this number and you get -3, it's z goes down by 3 units for every 1 unit change in x. When I compute the partial of f with respect to y, it looks like this time at that point it's going up a little bit. let's say, just for example, that y is equal to, or the partial of f with respect to y is equal to 2 units in that direction. Now these are just examples. I'm just throwing numbers out there. If you're wondering, Miss Townsend, where'd you get those units from, or where'd you get those numbers from? I'm just making them up so that we have something to interpret. This says, as y changes by 1 unit, z goes up by 2 units. For every 1 unit change in y, z is going up by 2. But that's at an instant. In the next instant, as y changes by a little bit, the slope is probably going to be different. That's okay. But that's what these are. These are instantaneous rates of change of the function in the x direction and y direction, which we're interpreting as slope at a point. If these values happen to be -3 and 2, this says for every 1 unit change in x, z goes down by 3 units. And this says for every 1 unit change in y, z goes up by 2 units. Okay, so similarly, when I'm looking for the slope in not the x direction or the y direction, but an arbitrary direction, I want to know what happens to the z value as I go in this direction. Like, what's the slope there? Z goes up or down by how many units as I go 1 unit in this direction? I don't want to go 5 units in this direction. I just want to go 1 unit in that direction. Then I want to see what z is, or how z is changing. So that's going to give us, that's the slope in that direction. This quantity that I'm talking about, the slope in the direction of a vector u hat. So it's the slope of the surface, provided that we're talking about z as a function of x and y, which gives us a surface. The slope of the surface in the direction of the unit vector u hat is called the directional derivative of f. And I guess we need to specify a particular point. We want the slope of the surface in the direction of u hat at x naught y naught. That's the directional derivative of f at x naught y naught in the direction of u hat. So when you see directional derivative, know that we're talking about slope. This is slope in the direction of u hat. Since it's slope, it's a scalar. It's not a vector. Directional derivatives are numbers, and they tell you how much z is going up or down as you go 1 unit in that direction, the direction given by u hat. Okay, so I'm going to give you a formula for this, and then we're going to do some calculations. We're going to do this example on the left. And here's the notation. If I want the directional derivative of f at x naught y naught in the direction of u hat, we write it this way. It looks like d with a little subscript u hat. Got f of x naught y naught to the right. And that is equal to this. This is the partial of f with respect to x at x naught y naught times the x component of u hat. So I guess we need to write u hat as a vector with components u1 and u2. So I'll do the partial of f with respect to x times u1 plus the partial of f with respect to y at x naught y naught times u2. And that's our directional derivative. And we're going to come up with an even shorter way of saying that same thing in just a little bit. Okay, so in order to calculate something like this, I need slope in the x direction at that point, slope in the y direction at that point, and I need a unit vector that's heading in the direction that we want to go, in the direction that we're interested in, trying to find the slope in that direction. So here's a particular function. I've got z equals f of x, y, which is the natural log of x squared minus y. That's a surface. And we are interested in this surface near the point x naught y naught equals 2, 3. So first we're asked to find the slope in the x direction at 2, 3. And that's going to help us do the directional derivative in a little bit. So let's find the slope in the x direction first. First, we get a formula for the slope in general. The formula for this slope is the partial of f with respect to x. So we want to compute that partial. So the partial of f with respect to x is the derivative with respect to x of natural log of x squared minus y. Now remember, this is not a product. You can't just have an ln by itself. You have to take the natural log of something. So this requires the chain rule. I've got a function inside another function, so I have to use the chain rule here. This is my inside function. Now since my inside function depends on x, I have to use the chain rule, and when I take the derivative of this with respect to x, treating y as a constant. So remember how the chain rule works. First we take the derivative of the outside function. The derivative of natural log of a function is 1 over that function. And then we multiply by the derivative of the inside by the chain rule with respect to x, treating y as a constant. Derivative of x squared with respect to x, it's just a power rule. We bring the 2 down, multiply by x to the 1 less power. X to the first is just x, so you didn't have to write the 1 there if you didn't want to. The derivative of y with respect to x is 0. So we've got this. We've got 2x. If you prefer, you can write it as 2x over 1 times this, multiply straight across. This is a formula for the slope in the x direction at any point xy in the domain of this function. You can plug in that particular xy and it's going to give you the slope in the x direction on the surface here. We want the slope in the x direction at x equals 2, y equals 3. So we compute the derivative, which is our formula for the slope, and then we evaluate the derivative at the point of interest to get the actual slope in the x direction at that point. So we'll say slope in the x direction at x equals 2, y equals 3 is equal to this partial of f with respect to x at 2, 3. So I replace my x with a 2. I replace my y with a 3. 2 times 2 is 4. 4 minus 3 is 1. So the slope in the x direction is 4. What does that mean? Well, that means the z values on my surface go up by 4 units for every 1 unit change in x when we're sitting at this point. When we're sitting at the point x equals 2, y equals 3, and z equals f of 2, 3, whatever that value is. Okay, so that's slope in the x direction. Now let's find slope in the y direction. And we'll come back to this little box over here in a little bit. So we're going to need it to calculate the slope in this direction, the direction of this vector over here. So let's do slope in the y direction. First we find a formula for the slope. The formula for the slope in the y direction is just the partial of f with respect to y. So we compute f sub y. So the partial of f with respect to y is the partial derivative with respect to y of my function. I'm just writing it down, reminding myself what I'm taking the derivative of. Since there is a y inside this logarithm, this is the inside function, the logarithm is the outside function. We have to use the chain rule to take its derivative. The derivative of log of a function is 1 over the inside function times the derivative of the inside with respect to y, treating x as a constant when we're taking partial derivatives. Since there is no y here, this x squared might as well be a 3 squared. It might as well be a 9. the derivative of this constant with respect to y is just 0. I know you want to do 2x, or a lot of students want to just write 2x there. Don't do it. That's not a variable at this point. We're treating it like a constant. Derivative of a constant is 0. And the derivative of negative y with respect to y is negative 1. So I end up with a negative 1 times this fraction, or if you prefer, just put the negative 1 in the numerator. And that's our slope in the y direction at that point, or excuse me, in general, not at the point. This is a formula for the slope in the y direction. If I plug in any xy in the domain of this function, it's going to give me this slope in the y direction at that point. Now if I want the slope in the y direction at x equals 2, y equals 3, the next thing we need to do is evaluate that partial with respect to y at 2, 3. That's the slope in the y direction at that point. So we've got negative 1 over, replace the x with 2, the y with 3. 4 minus 3 is still 1, so we have negative 1 over 1. So our slope in the y direction is negative 1. Again, what does that mean? Instantaneously, at this moment, at this particular point on the surface, the slope is negative 1 in the y direction. So as y goes up by 1, z goes down by 1. The tangent line of that curve of intersection between the plane x naught equals 2 and the surface, where the y is changing but the x isn't. That slope of the curve is negative 1. As y goes up by 1, z goes down by 1. Okay. So it's slope in the x direction, slope in the y direction, 4 and negative 1. So we did this part, and we did this part. Now we want to find the slope of the surface in the direction of this other vector. They say go 1 unit in the x direction and 1 unit in the y direction. Go along that little diagonal. How much is z changing along that diagonal? Well, in order to do that, we have to use this formula for the directional derivative. Okay. So there's my formula. And I've got z equals f of xy equals natural log of x squared minus y. And we want the directional derivative, or the slope of the surface, in the direction of this vector v equals 1, 1. At a particular point. So we're heading in this direction from the point where x equals 2 and y equals 3. That's our x naught, y naught. Now z has the corresponding z value. It's natural log of 2 squared minus 3. Natural log of 1. So I guess z equals 0 at that point. We want the slope of the surface at that location in this direction. Well, that's called the directional derivative. Anytime you're looking for slope, you're looking for the directional derivative. If you're looking for slope in the x direction, the directional derivative happens to be just the partial of f with respect to x. If you're looking for slope in the y direction, the directional derivative happens to be the partial of f with respect to y. If you're looking for slope in a different direction, your slope is given by that formula. Okay, so first of all, notice that they gave us a v that is not 1 unit long. We need a unit vector because of the way slope works, or the way we interpret slope. We always want to know, if this is our unit vector, we want to know what happens to the z values on the surface as we go 1 unit in this direction. Not 5 units in that direction, but 1 unit in that direction. If the vector is the wrong length, we're going to get the wrong slope. So we got to do something different. So you've got to find the unit vector in that direction first. So that's our first step. And that's easy enough to do. You just find the length of v and divide by it. So v is a vector with components 1, 1. So its length is 1 squared plus 1 squared, and take the square root. Remember, whenever you're finding the length of a vector, you take the components, you square them, add them, and take the square root. And so we get square root of 2 for our length. So that means our unit vector is the vector v divided by its length. So that's the vector 1, 1, and each of the components is divided by square root of 2. You could rationalize and call that square root of 2 over 2, but you don't have to. Now this is the unit vector in that direction. Well then, according to our directional derivative formula, we're just going to substitute in all of our pieces. We're just going to compute the the directional derivative of f at 2, 3 in the direction of u using the formula. And so this is, according to my formula, x naught y naught was 2, 3. The partial of f with respect to x at 2, 3 times u1 plus the partial of f with respect to y at 2, 3 times u2. We're just going to substitute in all of our values. Well, remember what we did earlier. Slope of the surface in the x direction at that point was 4. And u1, that's the first component of our vector u, so we just multiply. u1 is just 1 over square root of 2, so we're going to multiply by that. And then we're going to add the slope of the surface in the y direction. We already calculated that. That was -1. And I multiply that by the second component of u2. Or excuse me, that second component of u, which is called u2. And then when we multiply, we get 4 over root 2 minus 1 over root 2, which is 3 over root 2. You could call that the slope. That would be fine. If you prefer, you can also rationalize. So we get 3 root 2 over 2. What is that number? Well, that is the slope in the the slope of the surface given by z equals natural log of x squared minus y in the direction of the vector v at the point x naught y naught equals 2, 3. So we start at 2, 3, we go 1 unit in the x direction, 1 unit in the y direction, and we find a plane that intersects our surface that goes in that direction. And then we say, how much does z change in that direction? It turns out that z changes by 3 square root of 2 over 2 units per 1 unit change along that direction. Now I wanted to get a calculator out so that I could approximate this. I've got 3 times root 2 divided by 2. My calculator's nice. It gives me exact answers. Press this little SD button. Ooh, that's a glare to get a decimal approximation. So we've got approximately 2.12 as an approximation. So as we go 1 unit in this direction, the slope of the surface goes up by the z values on the surface go up by about 2.12 units. Okay. Now, I don't know about you, but when I was doing that, it felt like a dot product, didn't it? I took this partial of f with respect to x, and I multiplied it by the x component of my u. And then I took the partial of f with respect to y, and I multiplied it by the y component of my u. So there's got to be a simpler way involving dot product, and there is. The directional derivative formula can be restated in terms of a vector called the gradient of the function. the gradient of a function of two variables. It's written this way. You read this as del f, and it's a vector whose first component is the partial of f with respect to x and whose second component is the partial of f with respect to y. So I've got a formula for the slope in the x direction as my x component and a formula for the slope in the y direction as my y component. And this is our vector. Now, in this chapter, whenever you have a function of several variables, it really doesn't make sense to talk about a single derivative. If you've got two variables, you've got two partial derivatives. If my function was a function of three variables, maybe x, y, and z, I'd have the partial of f with respect to x, y, and z in my gradient. This vector of first partials is the multidimensional analog of the derivative. I'm going to show you the 3D version of Taylor series for a function, and you're going to see wherever there would have been an f prime, that's the gradient shows up. So this is playing the role that the derivative used to play. We just can't do it. It's not a single number anymore or a single function of x anymore. Because we've got multiple variables, it's a vector with multiple parts. So this is our multi-dimensional analog of the first derivative. And we'll have different versions of the gradient for more variables, but we'll get back to that later. So let's say now we know what the gradient is. We've got this vector. It's got these partials as its components. Now I can restate the directional derivative of f at x naught, y naught in the direction of u hat. The directional derivative was given by this formula, and remember, directional derivative means slope. I'll write it out this time. Directional derivative of f at x naught, y naught in the direction of u hat. And it's written this way: d sub u hat of f of x naught, y naught. And look at these two components. I'm taking u hat, which has components u1 and u2, and I'm dotting it with the gradient at 2, 3, or x naught, y naught in general. So I'll take gradient at x naught, y naught and dot it with u hat. That's the way I typically evaluate a directional derivative. First, I find the gradient, I plug in the point, I find the unit vector, and then I dot them. And this actually works not just for functions of two variables, but for functions of n variables, as many variables as you want. You'll find the gradient, you'll find a unit vector in the direction that you're interested in. If you have n variables here, the unit vector will have n components. And then you dot these two guys, and that's going to give you what I would call the slope of the surface in that direction if we're talking about z equals f of x, y. Maybe it's a slope of a hypersurface in that direction for more variables, but we can't really see it because we can't graph in 4D. Okay, so that's directional derivative. And directional derivative, again, is giving you slope in the direction of u hat. So we go in this direction of u hat, we intersect a plane that goes in that direction with our surface, and then we say, what is the slope there? Now what if I'm at a particular point, x naught, y naught, and I want to maximize the slope? Maybe I'm sitting here, and I want the slope to increase as much as possible. To find the maximum slope, well, that means I've got to maximize my directional derivative. So let's look at it. I want to maximize this now. Well, it's easier to maximize this if I write this in a slightly different form. Remember when we studied dot product, there were two ways of doing it. If I have these two vectors, the gradient and u hat, I can dot them by multiplying their components, multiply component by component, and then add. Or I could find the dot product with geometric information. The geometric definition of the dot product of u and v was the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. But this unit vector, this u hat is just a unit vector, so its length is 1, so that's gone. So now I've got the magnitude of the gradient times cosine of theta. Now if I want this directional derivative to be as large as possible, well, I don't really have any choice about the gradient at that point. I can't maximize that, but I can maximize this cosine of theta. The largest cosine of theta can be is 1. Cosine of theta is always between -1 and 1. So the maximum value of the directional derivative, which is the maximum value of the slope of the surface in that direction, or excuse me, maximum value of the slope of the surface at that point, is given by the magnitude of the gradient, and this occurs when the cosine of theta is equal to 1. Now remember, when cosine of theta equals 1, cosine of theta equals 1 when theta equals 0, and lots of other times, but the one we're probably most interested in is 0 degrees or radians, either one is fine. What does that mean? Remember, when you use the dot product formula, this angle, theta, is the angle between u hat and the gradient. If the angle between u hat and the gradient is 0, that means u hat and the gradient are pointing in the same direction. The gradient is longer, but or generally it's longer. This is a unit vector, but yeah, if the angle between them is 0, they're pointing the same way. U hat is going this way, and then maybe the gradient is also going that way. At that particular point in the xy plane, we've got x naught, y naught, and z naught, or z equals 0. So we're in the xy plane. Maybe it looks like this. There's some surface above this xy plane. And here's x naught, y naught, 0. That's the direction that we want to go. And the gradient is heading in that direction whenever theta is equal to 0, because the angle between u hat and the gradient is 0. Okay, so that's very insightful. So the maximum value of the directional derivative, which is the same as the maximum value of the slope of the surface, at x naught, y naught, turns out to be the magnitude of the gradient at that point. Now let's say you're trying to figure out which direction do I go to get this maximum, which direction do I go to get this maximum slope? Well, you go in the same direction as the gradient. So we've got the maximum slope of the surface at the point is just the magnitude of the gradient. And that means, I don't know why I put equivalent there, that means, and the magnitude of the gradient, and that happens when cosine of theta equals 1, and that happens when theta equals 0, and that means that u hat and the gradient are in the same direction. So the direction that you go to maximize the slope is the gradient, is in the direction of the gradient. So that means that the gradient of f, we said, is the direction that you should go from the point x naught, y naught to maximize the slope, to increase your slope as much as possible, or to have the maximum slope possible as you go along the surface. And that's a very wordy way to say go that way and the z-values will go up as much as possible from x naught, y naught. Another way of saying that, and the way that it's typically said, is that the gradient of f at x naught, y naught is the direction of steepest ascent. And I'm emphasizing ascent because I'm going to talk about descent later, but I know I'm putting the emphasis on the wrong syllable. So this statement over here is equivalent to saying the gradient at x naught, y naught is the direction of steepest ascent. Sometimes you'll hear me say ascent to distinguish it from descent, which we'll talk about in a minute. Okay, so you're standing on a mountain. You're standing at a particular point, x naught, y naught, and the corresponding z-value, and you say, which way should I go to maximize my slope? Well, you go this way. You go in the direction of the gradient. And as you go in that direction, the slope of the surface is going to be given by the magnitude of the gradient. So let me write that down. Now this is slope. Maximum slope of the surface at x naught, y naught is given by the magnitude of the gradient. That's a scalar. When you're done, if I ask you for the slope of the surface, you should give me a number back. You should give me, the slope is 5. Go that way, z is going to go up by every 5 units for every 1 unit change in that direction. Now, the direction of steepest ascent, that's the gradient at x naught, y naught. Now some people might say, that's not direction. Direction's supposed to be 1 unit long. Yeah, that's what the author of the Thomas textbook says, but I've heard direction referred to in lots of different ways. If you give me a vector, to me it indicates direction. So the gradient is the direction of steepest descent. Make sure you remember this gradient is a vector. It's not a scalar. It does not tell you the slope. Not until you find its magnitude. Its magnitude is the slope. The gradient points in the direction that you should go. To increase z from your x naught, y naught, f of x naught, y naught, from that point in 3-dimensional space as much as possible. And make sure you see that the gradient, if this is a function of 2 variables, the gradient only has 2 components. So this is the partial of f with respect to x at x naught, y naught, and the partial of f with respect to y at x naught, y naught. That's the gradient evaluated at a particular point. It corresponds to a vector in the xy plane. Maybe we're talking about an elliptic paraboloid. Maybe we're talking about something that looks like this. If you're here at this point, and you're trying to figure out, well, which way should I go to increase z as much as possible? You might have to go like in this direction, something like that. But this vector has no z component. It's not like it's pointing up over here. This is saying, keep going that way on the surface, and then the z's are going to go up as much as possible. Okay, so that's direction of steepest ascent. Now let's say you want to minimize the slope of the surface. And when I say minimizing the slope, I mean like the minimum value of the slope. I know sometimes people think minimum value of the slope, they think no slope, no steepness at all. That's not what we're talking about. Negative slope is smaller than zero slope. So if I want the minimum slope of the surface, let's say, the gradient says head in this direction. If you're standing here, go that way to increase the z-values as much as possible. How can you decrease the z-values as much as possible if you're standing on a mountain? Here's our mountain. I'm not very good at drawing mountains. Looks like a Reese's peanut, or a Hershey's Kiss, excuse me. So the slope increases as much as possible. It says go that way. Well, how do you decrease as much as possible? You go in the opposite direction, right? So the maximum slope was this. The minimum slope is the opposite of that. Now we could also derive the minimum slope looking at our directional derivative formula again. So remember, directional derivative of f at x naught y naught in direction of u is the gradient dotted with that unit vector u heading in the direction. This is the slope in the direction of u hat. By the geometric definition of the dot product, that's the same as the magnitude of the gradient times the magnitude of u hat, it's a unit vector, so that's 1, times the cosine of the angle between them. So the smallest that this directional derivative could possibly be occurs when cosine of theta equals -1. So the minimum value of the directional derivative is this times -1 and again that occurs when cosine of theta is -1, and cosine of theta is -1 when theta equals pi radians or 180 degrees, whichever one you prefer. So the gradient was saying go that way, and it's actually a vector in the xy plane. It's saying down here, if you head that way, the z-values are going to increase as much as possible. Question says, well, how do I minimize the z-values as much as possible? Where's the steepest slope in the opposite direction? Well, it turns out you just go in the opposite direction. Go that way instead. So you're going to change your vector by 180 degrees. So the minimum value of the directional derivative is -1 times the magnitude of the gradient, and the direction of steepest descent, that is where the slope of the surface is as steep as possible, but it's negative. That's given by the opposite of the gradient vector. So the negative gradient at that point is the direction of steepest descent. I keep emphasizing descent. That's not normally how you say it. Direction of steepest descent. But I just want to distinguish it from direction of steepest ascent up here. If you want to have the maximum slope of the surface, go this way, and that's what the slope is going to be. If you want the minimum slope of the surface, go this way, and that's what the slope is going to be. Now, the direction of steepest descent points in the direction that you should go. To make z decrease, as much as possible, from the point where you're at, from x naught y naught, and the corresponding z value, f of x naught y naught. This is local information. It doesn't necessarily point to the bottom here. It's just going to point in the steepest direction that you can, the steepest, or it's going to point in the direction of steepest slope, steepest negative slope. on the surface. But if I go a little bit in that direction, it's the new gradient vector is going to point in a different direction. So just make sure you understand that this is local information. It does not necessarily point to the bottom of the surface, and the direction of steepest ascent does not necessarily point to the top of the surface. It's saying if you're standing here on a mountain and you're looking for where the z-values increase the most and where they increase the least, the gradient tells you where they increase the most. If you go that way, the z's go up the most. The opposite of the gradient tells you if you go that way, the z's go down as much as possible. So let's go back to our example. We had this function, this surface, and we were interested in the slope of the surface near x, y equals 2, 3. Remember, make sure you know the minimum slope of the surface is this. That's a scalar. And the direction you should go to get that minimum slope is the opposite of the gradient at that point. Okay, so here is our function, which represents a surface. Every xy is associated with a z. Let's say we want to find the maximum slope of the surface at 2, 3 and the minimum slope of the surface at 2, 3. And we should also find direction of steepest descent and direction of steepest descent. Now we're probably going to do this one first. It's a little out of order. Okay. And we want direction of steepest ascent and descent at the point 2, 3. Okay. Well, we've already done most of the hard work for this. We've got the gradient of f at 2, 3. That's the partial of f with respect to x times I hat plus the partial of f with respect to y times j hat. We evaluate each of those partials at 2, 3. Now we did this work a while ago. The partial of f with respect to x turned out to be 2x over x squared minus y. The partial of f with respect to y turned out to be negative 1 over x squared minus y. So that's the gradient in general. It's the multidimensional analog of the first derivative. Now if I want to know the slopes of the surface in the x and the y direction at 2, 3, I plug in 2 and 3 for x and y. We've already done that, so I'm not going to do it again. But when I plug in 2 for x and 3 for y, I get 4 for the slope in the x direction, and I get negative 1 for the slope in the y direction. We've already done that. Now, according to our calculations, this is the direction that we should head in to maximize the slope as much as possible. So this is the direction of steepest ascent. You should go this way, and the z-values on the graph of natural log of x squared minus y are going to increase as much as possible from this point 2, 3. Now, if you want to find the slope in that direction, you just find the magnitude of the gradient at 2, 3. So I've got the square root of 4 squared plus negative 1 squared. So 16 plus 1 is 17. So we get square root of 17. And we all know that that's a little bit more than 4, but let's see what the decimal approximation is. So it's about 4.12. So the maximum slope of the surface is 4.12. And the direction I should go to make z increase by 4.12 for every 1 unit change in that direction is given by this function, or given by this vector. Now if I want a unit vector in that direction, well, I have to divide by the magnitude of this, which I'll have to divide by square root of 17. That's going to give me the unit vector in that direction. So this is the direction of steepest descent, and that's the maximum slope. Well, what's the minimum slope? Well, if the maximum slope is 4.12 approximately, square root of 17 units, units per unit, the minimum slope, and we have to head in this direction to get that slope. The minimum slope comes from heading in the opposite direction. So take this and multiply by -1. If the z-values are going up by 4.12 as I go this way, if I turn around on my mountain, they're going to go down by 4.12 in the opposite, or in the other direction, the opposite direction. So the minimum slope at 2,3 is the negative magnitude of the gradient at 2,3. So it's negative square root of 17, which is negative 4.12. And the direction that you go to minimize that slope is the direction of steepest descent. And the direction of steepest descent is given by the negative gradient of f at 2,3. So I just take my gradient vector and I multiply it by -1. So I get x, we go -4 units in the x direction, 1 unit in the y direction to make our z-values decrease as much as possible, and they're this amount. Now this is the minimum slope, and that's the maximum slope. So that means at every level in between, for every unit vector in between this vector, which points in the direction of steepest ascent, and this vector, which points in the direction of steepest descent, all the slopes are going to be between -4.12 and positive 4.12, or between negative square root of 17 and positive square root of 17. So we're here. Increase as much as possible, you get 4.12. Decrease as much as possible, you get negative 4.12. Any other slope, if you go any other way, it's not going to be so bad. It's not going to be so steep. You don't have to go up or down 4.12 units for any other direction from there. Okay. So one last thing that we'll say about gradient. Well, we talked about steepness. If I want that slope to be as steep as possible, I go in the minimum direction or the maximum direction. Any ideas on how we could get a zero slope out of this directional derivative? Well, we get a zero slope. Watch this. When, remember, this dot product is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. And the directional derivative, again, represents slope at x naught, y naught in the direction of u hat. And this is 1. I can make this 0 by making cosine of theta 0. So that happens when theta equals 90 degrees, or pi over 2 radians if you prefer. What does that mean? That means the gradient at that point and u hat meet at 90-degree angles. And actually, I think that makes a lot of sense. Let's look at our mountain again. Where did our mountain go? There's our mountain. If I go this way, I increase my z's as much as possible. If I go this way, I decrease my z's as much as possible. What if I don't want to increase my z at all? What if that sounds like a lot of work, and I'm trying to avoid work? Maybe I just want to stay here at z equals 10 all the time. I just want z to be a constant 10. I don't want to have to go up any higher or lower on the mountain. Well, then I go in a perpendicular direction. I know this one doesn't look quite perpendicular to these guys because they have a z component, but if one is telling me to go that way and the other one's telling me to go that way, and I would head in I would go in a direction that's at a 90-degree angle from the original gradients to make my z's stay constant. And my z's are staying constant when I have zero slope. So, okay, what does that mean? Well, that means the gradient is always perpendicular to the level curve. And this looks a little strange, but bear with me. It's the level curve given by z naught, which is f of x naught y naught, equals f of x y. I know that looks very strange, but this is just a number on this side. We're setting z equal to a constant, and this is the rest of the formula for the surface. So our gradient vector is always perpendicular to level curves. Let's say our level curves look like this. If the gradient is telling me to go this way to increase my z values as much as possible at that x naught y naught, this is f of x y equals z naught, where z naught is f of x naught y naught. That's that location. We're in the xy plane looking at a level curve. And I think that makes sense. If I want the z's to stay constant, I go in that direction. I go in that perpendicular direction. Now it's only constant for a moment because the level curve is curving. But our gradient is always going to be perpendicular to that. Yeah, and the reason why they have to be perpendicular is because the only way this dot product is zero is if u hat, the direction we're interested in the slope in, and the gradient meet at a 90-degree angle. So I think just intuitively it's a better way to look at it. If I want to increase as much as possible, I go this way. If I want to decrease as much as possible, that's the direction of the gradient. If I want to decrease as much as possible, I go the opposite way, and the z's go down. If I want my z's to stay constant, I go in a perpendicular direction. Then I'm saying on a level curve. So my level curves are always perpendicular to the gradient. Okay, and we'll probably see some more examples of that in the next section when we start talking about tangent planes. Yeah. We'll look at gradient vectors of level surfaces, of functions of two variables there.